What's up, everyone? Welcome back to CyberForgeAI. Take a seat, get comfortable. In this class, we aren't learning how to code, we are learning how to build efficient code. We are going to become algorithm architects. We're going to master Big O notation. So, without further ado, let's begin our class on time and space complexity.
Imagine looking up a friend's number in a phone book. Now imagine that phone book has 1 billion pages. Manually flipping through a stack of paper that thick to find one specific name is physically impossible. If you had to try, the most basic way to do it is page by page. You open to page 1, check if the name is there, and if it isn't, you turn to page 2. You repeat this process until you finally find the right number. In computer science, we always plan for the worst possible outcome. In this case, the worst case is that the name you want is sitting on the very last page of that massive book. You would have to turn every single page to get there. To talk about how good or bad a strategy is in that worst-case scenario, programmers use a grading system called Big O notation. It measures how a system handles a workload as that workload gets bigger. To measure how much time a task takes to finish, we use a grade called O of n. On this graph, we are plotting the time it takes to search against the total number of pages, which we call n. This creates a perfectly straight diagonal line. This straight line represents a one-to-one relationship. If the book size doubles, the time required to search it also exactly doubles. These linear algorithms are very predictable, but they become extremely slow when a problem grows to include millions or billions of items. This manual page flipping is exactly how a standard for loop works in code. The computer looks at the first item, then the second, then the third, checking for a match every time. This simple block of code behaves exactly like a human flipping pages. It runs 10 times for a 10-page book, and it runs 1,000,000 times for a 1,000,000-page book. But there is a much faster way to search. Instead of page by page, you can open a book directly to the middle. If the name is further back, you can simply tear out the first half of the book and throw it away. You take the half that is left, open it to the middle again, and check the alphabet once more. By throwing away the wrong half over and over, you narrow down your search incredibly fast. We call this O log n. That word log is just a mathematical way of counting how many times we can split the book in half before we reach a single page. With every single step, the amount of work left to do is cut right down the middle. Look at the difference on the graph. While our first method creates a steep climbing line, this halving method creates a curve that stays very low and flat. It takes almost the same amount of time even as the data grows massive. Choosing a better algorithm changes the entire trend of a program. It is the difference between a task being impossible or happening almost instantly. Speed is only half the story. We also have to consider how much physical room your computer needs to get the work done. Imagine every time you flip past a page, you must write the name of every skipped person on a physical notepad. As the book gets bigger, your list gets longer, and you need more and more paper. This is what we call space complexity. It measures how much extra working memory, the computer's temporary storage space, is required as the data grows. Here, the memory we need grows at the same diagonal rate as the book size. Now, imagine if you didn't use a notepad at all, if you just remember the name of the person on the current page and forget it when you turn to the next one. The amount of brain power you need stays the same. The diagonal line on the graph drops until it is perfectly flat. We call this flat line O of 1, or constant space. It means your memory footprint is completely isolated from the size of the data. Whether the book has 10 pages or 10 billion, you only ever need room for one name. You want a program that is lightning fast, but you also want it to fit perfectly within the physical memory your computer has available. Big O notation isn't about counting the exact seconds on a clock or the precise number of megabytes on a chip. A brand new computer will always be faster than an old one, no matter the code. Because hardware is always changing, Big O only measures the mathematical trend of the algorithm itself. This math is how modern technology scales. Platforms like YouTube and social media networks process billions of data points every single day. If a global database used a slow, page-by-page algorithm, a single search would take days to complete. By using algorithms that slice the problem in half, those same systems find what you need in milliseconds. Understanding complexity is simply asking a question. Does this process check every single page, or does it cut the problem in half? And how big of a notepad does it need to finish the job?
And that is how you keep your code from melting your servers. If this breakdown of time and space complexity made sense, make sure you smash that like button and subscribe to the channel.